Voyager 1. The fight to keep humanity's farthest spacecraft alive. Somewhere far beyond the planets, a spacecraft launched almost 5 decades ago is still communicating with Earth. It was built in the 1970s, designed for a mission that was expected to last only a few years. Yet Voyager 1 has continued traveling through space long after its original mission was supposed to end. Today, however, its survival depends on decisions that have to be made from billions of miles away. A command sent from Earth can take nearly an entire day to reach the spacecraft. Then engineers have to wait for the response before they know whether their decision worked. One mistake could potentially end decades of scientific discovery. Voyager 1 was launched on September 5, 1977, from Florida. Its original journey was designed around the outer planets. It passed Jupiter in 1979 and Saturn in 1980. After that, instead of stopping, Voyager 1 continued outward. There was no final destination waiting for it. It simply kept moving away from the Sun. For decades, the spacecraft continued operating while gradually traveling farther into unexplored territory. Then, in 2012, Voyager 1 reached a milestone unlike anything achieved by another human-made object. It crossed the heliopause, the outer boundary of the Sun's protective bubble. Beyond that boundary lies interstellar space. For the first time, a human-built spacecraft was directly measuring the environment between the stars. Today, Voyager 1 is more than 15 billion miles from Earth. At that distance, sunlight is far too weak to provide useful electrical power. So Voyager never depended on conventional solar panels. Instead, it receives electricity from radioisotope thermoelectric generators. These systems produce electricity from the heat released as radioactive material slowly decays. When Voyager 1 left Earth in 1977, its power system produced roughly 470 watts. But radioactive decay is gradual, and the spacecraft's available electrical power has been declining year after year. That decline was always expected. The engineers knew that eventually Voyager would reach a point where there simply would not be enough electricity to operate everything. The solution has been to sacrifice systems one at a time. Every instrument consumes power. Every heater consumes power. Even systems that seem unimportant can generate heat that helps protect other components from the extreme cold. So shutting something down is never as simple as pressing an off switch. Engineers have to determine what can be sacrificed without damaging something even more important. That process has already claimed several of Voyager's original instruments. In February 2025, NASA switched off the spacecraft's cosmic ray subsystem. The instrument had spent decades studying energetic particles coming from the Sun and from deep space. Turning it off meant losing another scientific window into interstellar space, but the power saved could help keep other systems alive. Then came another warning. During a routine maneuver later that month, Voyager 1 experienced an unexpected drop in electrical voltage. The spacecraft rotates occasionally so its antenna can remain correctly pointed toward Earth. During this particular maneuver, the power level approached a threshold that could have triggered Voyager's automatic protection system. That system is designed to protect the spacecraft when something goes wrong by reducing its power consumption. The problem is that Voyager is now so distant that recovering from an unexpected automatic shutdown is extremely complicated. Engineers managed to respond before the situation became worse. But the incident demonstrated how narrow Voyager's remaining power margin had become. The team knew they needed another solution. Then, in April 2026, NASA made another difficult decision. The low-energy charged particle experiment was switched off. That instrument had survived for nearly half a century and had completed millions of internal mechanical movements. Even after its supplemental heater was disabled to conserve electricity, the instrument continued functioning at extremely low temperatures. Its shutdown represented another major loss for the mission. After that decision, Voyager 1 was left with only two operating science instruments. One is the magnetometer, which measures magnetic fields surrounding the spacecraft. The other is the plasma wave subsystem, which detects waves moving through the thin plasma of interstellar space. Those remaining instruments are incredibly valuable because there is currently no replacement spacecraft making the same measurements from that region. But NASA's engineers were not ready to accept that Voyager was nearing the end. They had been developing another strategy. Inside the team, the plan became known as the Big Bang. The name reflects how ambitious the procedure is. Rather than simply turning off one instrument, engineers planned a carefully coordinated reconfiguration of several spacecraft systems. Some older equipment would be disabled. Certain heaters would be changed. Other systems would take over tasks that had previously been handled differently. The goal was to reduce the spacecraft's annual power requirements while keeping critical components warm enough to continue operating. That temperature problem is especially important. Voyager is traveling through an environment that is unimaginably cold. Voyager 1. The mission that refuses to go silent. Voyager 1 is now operating with only a fraction of the electrical power it had when it left Earth. That means NASA has been forced to make difficult choices. Instruments that once worked continuously for decades have had to be switched off one after another. Every shutdown saves energy, but it also means losing another scientific capability forever. One of the most important instruments recently sacrificed was the low-energy charged particle system. It had been working for decades, helping scientists understand energetic particles moving through the region beyond the Sun's protective bubble. The instrument's mechanical system had completed millions of movements during its lifetime. Even after its heater was turned off to conserve electricity, it continued operating in extreme cold. Eventually, however, the power situation became too difficult to ignore. NASA had to shut it down. That left Voyager 1 relying on just a small number of scientific instruments. Among them are the magnetometer and the plasma wave system. The magnetometer studies magnetic fields surrounding the spacecraft. The plasma wave instrument detects disturbances traveling through the extremely thin plasma between the stars. These measurements may sound abstract, but they are incredibly important. Voyager is collecting information from a region that no other spacecraft is currently exploring in the same way. And that is why NASA is trying something unusual. Engineers have developed a complicated power-saving strategy designed to squeeze additional life from the spacecraft. The idea is not simply to switch things off. Instead, several systems have to be changed together. Some equipment can be shut down completely. Certain heaters can be replaced with alternatives that consume less electricity. Other spacecraft systems can be rearranged so that essential components remain warm enough to operate. This is where things become extremely delicate. Voyager is traveling through an environment that is unimaginably cold. The spacecraft cannot simply stop producing heat. Some components depend on that heat to remain within their safe temperature range. So an energy-saving decision can create another problem. Saving electricity could potentially make another system too cold. That is why engineers have spent months modeling the spacecraft's behavior before sending commands. And instead of immediately testing the strategy on Voyager 1, they chose Voyager 2. Voyager 2 is also decades old and traveling through interstellar space. But because it is closer to Earth, commands and responses do not take quite as long. That made it a valuable test subject. NASA successfully demonstrated the power-saving procedure on Voyager 2 in 2026. The result was extremely important. It showed that the basic concept could work without immediately putting the spacecraft's remaining scientific systems in danger. Now engineers can use what they learned from Voyager 2 to prepare for Voyager 1. But Voyager 1 has its own complications. It is farther away. Its communication delay is longer. Its power situation is different. And every spacecraft behaves slightly differently after nearly 50 years in space. So even a successful test on Voyager 2 does not guarantee that Voyager 1 will respond exactly the same way. The team therefore has to proceed carefully. Before attempting the complete procedure, NASA is performing additional tests on Voyager 1. One of the most important questions is whether the spacecraft can maintain safe temperatures after the power changes. If the thermal conditions look good, engineers can move toward the full procedure. If everything works, Voyager 1 could gain additional operating time. That might allow its remaining instruments to continue collecting data for another year or potentially longer. There is also a particularly interesting possibility. The low-energy particle instrument that was previously switched off could potentially be restored if the new power configuration provides enough electrical margin. That would be an extraordinary comeback for an instrument that has already spent decades operating in deep space. But even if it never comes back, Voyager's existing measurements remain incredibly valuable. When Voyager crossed beyond the heliopause, it entered an environment humanity had never directly sampled before. The spacecraft discovered that interstellar space is not simply an empty, perfectly quiet vacuum. It contains plasma. It contains magnetic fields. It contains energetic particles. And it can still be affected by disturbances originating from the Sun. Scientists have observed changes in plasma density and magnetic field strength that appear to be connected with waves traveling outward from solar activity. These observations have helped researchers understand how the Sun's influence interacts with the environment between stars. Voyager has essentially become a moving laboratory. The laboratory is not inside a building. It is billions of miles away, traveling through darkness. And its instruments are operating under conditions no spacecraft on Earth can easily reproduce. That makes the data especially valuable. Another major contribution has involved cosmic rays. These high-energy particles travel throughout the galaxy. Inside the solar system, the solar wind and magnetic environment can affect what reaches our instruments.